All right. You had a worksheet. I asked you to start. That worksheet will be a continual progress in regards to homework. I ask you to just go through and write a null and alternate hypothesis and go through null and alternate hypothesis. We will continue to add to that what you'll be doing. So that worksheet there will be your homework for the next couple days here. We will just once again just continue to add. Okay, we are going through the idea of hypothesis testing. It is the final step in regards to statistical analysis because we want to, once again, we want to make educated guesses. Okay, a hypothesis and an educated guess, we want to make them, but we want to now statistically test that hypothesis that we have. Just like you go through experiments over chemistry and physical science, you test certain things. Okay, that's the idea we can do here with respect to hypothesis testing, but you're just doing everything mathematically. You're gathering data, you're dealing with statistical analysis, you're calculating the mean, the standard deviation. We will go through a statistical analysis of specific data that you have and test a hypothesis. Okay, just going through a couple more hypotheses on the idea of null and alternate hypothesis. The researcher wishes to test the claim that the average age of lifeguards is greater than 24 years. Okay, he wants to test a claim that the lifeguards in Ocean City are greater than 24 years. So looking at the null and alternate hypothesis, most of the time, okay, and once again, this is as you get more and more involved in statistics, you'll get more and more exposure to this. We're just going to talk about today. Most of the time, when you make a claim, when somebody makes a claim, that's what they hope is going to be true, and that goes normally into the alternate hypothesis. Okay, that normally where it goes. But if there's no really established value, which is what we have here, we have no really established value. He just thrown a number out there. The lifeguard in Ocean City is greater than 24 years. Okay, most of the time, like I said, that claim is going with the alternate hypothesis. But if there's something that is not established, that will take it into the null hypothesis. Because ultimately what we are doing is we are testing the alternate or the null hypothesis. That's what we are testing. So we're testing his claim. So we are either going to reject the null hypothesis or we will fail to reject that null hypothesis. Okay, and that's his claim. So it's sort of a unique situation, and most of the time it will be what we talk about or what we talked about on Friday. What he hopes is true is going to go into the alternate hypothesis. But when you're trying to test a value, that value that you're testing is going to go in the null hypothesis. A researcher claims the average cost of men's shoes is different than $80. Once again, when we're talking about null and alternate hypothesis, equality will always go with the null hypothesis. Or the null hypothesis. Equality will always go with the null hypothesis, and that's something to always remember. So when I'm trying to determine is different than $80, the key thing is looking at the description of what we're dealing with and comparing in comparison to the number. Okay, when you talk about the idea it's different, that's going to throw you into equal and not equal to. Or you're going to have greater than, more than, or less than. So when we talk about is different, and we're looking at the null alternate hypothesis, well, when I'm talking about is different, I'm going to have equal to and not equal to. Well, equality will always go with the the null hypothesis. Equality will always go with the null hypothesis. So that's going to throw the equality there, which means my ultimate hypothesis is not equal to the $80. Most of the time, the null and ultimate hypothesis will be pretty straightforward for you. Okay, sometimes there's going to be a little tweaks in there. We're limited in our amount of time that we had to deal with this, so I'll pretty much keep them straightforward. You'll be able to determine by the statements and the problem where my null and ultimate hypothesis is going to go. Statistical test uses data obtained from a sample to maintain or to make a decision whether the null hypothesis should be rejected. Okay, so we're going to do a statistical test, and we're going to come down to two solutions. We are either going to reject the null hypothesis or fail to reject the null hypothesis. It's going to be one of these two answers, and statistically you'll be able to determine, do I reject the null hypothesis or do I fail to reject the null hypothesis? Once again, most of the time the null hypothesis is something that's already established. There's a difference between the terminology. If I reject, I don't like it, we're going to get rid of it. Fail to reject, there's a difference between the idea of fail to reject and to accept it. If you fail to reject it, you still may not believe it, but you'll live with it for now. That's the idea of fail to reject. I might have to do some statistical analysis, some additional statistical analysis that allows me to reject it eventually. So you have two choices. You're either going to reject or you're going to fail to reject a null hypothesis. We have two types of errors that we're going to run into. The one that we're going to be dealing with mainly is type 1 error. When you get into the next level of statistics, if you get into that, you'll deal with type 2 errors a little bit more. Type 1 error, you reject the null hypothesis when it is true. You reject the null hypothesis when it is true. In the type 2 error, you do not reject the null hypothesis when it's actually false. You do not reject the null hypothesis when it's actually false. And you should reject it. We have a null hypothesis, a defendant is innocent. What would be the alternate hypothesis? What would be the alternate hypothesis to a defendant is innocent? That's your null hypothesis. Okay, he's not innocent, or he's guilty. He's not innocent. He's either going to be innocent or not innocent. What would be the type 1 error? What would be your type 1 error for this? Now, type 1 error, going back to definition, you reject the null hypothesis when it is actually true. You're going to reject the null hypothesis when it's actually true. What has occurred here? We are making an error. The jury is making an error. What would be the error?
They call the defendant guilty
Okay? Innocent person is found guilty. You reject the defendant being innocent. That means he's guilty. You ask most of the people out there in Mansfield, most of the people in jail, they will say, I am a victim of a type 1 error. I didn't do it, but I'm still sitting in jail. Most of those people out in Mansfield there. What would be your type 2 error? What would be your type 2 error, not type there? You do not reject the high null hypothesis when it's actually false. What would be the type 2 error? Go on. He's guilty, but he has been set. Yeah, he's guilty. He's a person guilty, but he's set free. A lot of people will say O.J. Simpson is a type 2 error. Just because a glove wouldn't fit. So you guys don't know. You've probably seen stories about it, movies about it. I got to live through it. Okay, where two years ago, you couldn't turn on TV at a news station without hearing about all the statistics about COVID. And it got to a point where you didn't even want to turn on the TV anymore because you heard so much stuff about it. When OJ was going through it, that was it right there. You turn on the news and it was all about that right there. Heck, it was prime time TV. They would put his court case on TV, his trial on TV. And because the glove would not fit onto his hand, he was basically set free. That was the deciding factor to most of the jurors. They had these gloves that were there that said the person wore these gloves. And OJ tried to put on the gloves, and it'd be like you putting on a set of kids' gloves. He couldn't fit them over his hand. But what they did is they gave him a bunch of things that made him retain a bunch of water. So his hands enlarged, and he couldn't get the gloves over his hands. Heated them up a little bit. Oh, yeah. Level of significance. Okay, we start getting into, hopefully we'll get into the actual calculations today. Level of significance, the maximum probability of committing a type 1 error. The probability is symbolized by alpha, and it's a probability, once again, of getting a type 1 error. And that's all we will be dealing with in Stats 1, is testing to see if we have a type 1 error. And we'll look at the level of significance of alpha. And alpha is just basically 1 minus your confidence interval. So if you have a confidence interval of 95%, your alpha value is 5% or 0.05. There's a value, second value, which is called beta, which is the probability of committing a type 2 error. The beta value, once again, stats 2 will take you into beta values. We don't do stats 2 here. You go to college, you get stats 2, you deal with beta values. You'll be given a level of significance, and that's what you'll be testing in every problem. Critical values. And this is what you'll be using, once again, your t-table for, to find critical values. Separate the critical region from a non-critical region. And you'll be, once again, using your t-table. Because in your t-table, you'll have, along the top here, once again, it will be prescribed for you. Your alpha values will be given to you. Okay, we'll talk about one-tail, two-tail tests here. And you'll be able to find critical values. Your critical or rejection region. Your critical or rejection region. It's a range of values of your test value that indicate there's significant difference and the null hypothesis should be rejected. You'll be doing a test value, and you'll put this test value on a bell-shaped curve. You'll have a range of values for your critical values. And if you fall into a region that's outside your critical values, you'll reject the null hypothesis. Your non-critical and non-rejection region, it's going to be the exact same thing. The only thing that's going to be changed is, should not be, the range of values of the test value that indicates a difference was probably due to chance, and the null hypothesis should not be rejected. So you're going to have test value, you're going to have this test value, and you're going to place it basically on a bell-shaped curve. Am I going to go into a critical region or a non-critical region? If it's in the critical region, I will reject the null hypothesis. If it's in a non-critical region, I will fail to reject the null hypothesis. So if you fall into a critical region, you'll reject the null hypothesis. If you fall into a non-critical region, you will fail to reject the null hypothesis. You got two scenarios that's going to happen. You're either going to reject it or you're going to fail to reject. Okay, we have two types of tests. You have a one-tailed test. Indicates the null hypothesis should be rejected when the test and the critical value is, or the test value is in the critical region on one side of the mean. Your one-tailed test will occur when you're dealing with less than or equal to and greater than, or greater than or equal to and less than. It will tell you you're going to be dealing with a one-tailed test. You can have a right tail or left tail. Okay, you have a right tail or left tail. What will determine which test you use is your alternate hypothesis. Your alternate hypothesis. When your alternate hypothesis is greater than, arrows pointing to the right, you're using right tail test. When your alternate hypothesis, as mu is less than, you're pointing to the left, so you're going to use your left tail test. So you look at your alternate hypothesis. That will tell you if you're using a left tail or right tail. Null hypothesis, you have a two-tail test. Null hypothesis should be rejected when test value is on either side of the two critical, or either test value is on either of the two critical regions. You have two critical regions. This occurs when you have your mu is equal to and not equal to. That will give you a two-tailed test. So we go back to your notes on Friday. You go back to your notes on Friday. And we were stating the null and ultimate hypothesis. First one, the examples on the back. Researchers think that expectant mothers use vitamin pills. The birth weight of babies will increase the average birth weight of a population, or birth weight of the population, or will increase. The average birth weight of the population is 8.6. We look at our null, and we look at our alternate hypothesis. Will this be a one tail or two tail? One tail or two tail? Alea, what would we have? Huh? The top one here. I'm looking at the notes from Friday.
Oh, sorry.
The notes from Friday. One tail, and which direction? Right. One tail right. Looking at alternate hypothesis, so it's going to be a one tail right. Engineer hypothesizes the mean number of defects can be decreased in the manufacturing process for CDs by using robots instead of humans for certain tasks. Mean defects is 18 per 1,000. Okay? Wrote the null and alternate hypothesis. Okay? One tail, two tail, Seth?
One tail.
One tail, left or right?
Left.
Left? Alternate hypothesis, one tail left. All right. The notes are posted. Psychologist feels that playing a soft music during a test will change the results of the test. He is not sure if it will increase or raise or lower. In the past, mean was 73. One tail, two tail. Okay, Mullen? Two tail? Okay, because we have equal to, not equal to. Chemist invents an additive to increase the life of a car battery. The manufacturing lifetime car battery is without the additive is 36. One tail and two tail. Derek?
One tail.
One tail, left or right? Right? Okay, last one. Contractor wishes to lower heating bills by using special type of insulation house. Average monthly bill is 78. One tail, two tail, Abby? One tail, left or right? Okay? Easy thing to determine. Now, if you pull out your T-table, now. If we look at the T-table, along the top side of the T-table, what we have dealt with and worked with so far is just the confidence interval. Now, if we look at the next two rows below the confidence interval, the next two rows on the T-table on the confidence interval.
T-table.
Yep. If you look at your next two rows, what you're given is a one tail and two tail, and then a corresponding alpha value. Okay? So your alpha value will be given to you within a problem. With the null and alternate hypothesis, you have to determine is this a one tail or two tail test. Okay? Your critical values are going to all lie within this table now. These critical values that will be determined lie within this table. We will start out with a z-test. We'll be given a z-test these Z values right here, these values right here, lie along the very bottom of your t-table. So if I have an alpha value of 0.10, so I have a one tail alpha value of 0.10. So I go over to the second column there and take that all the way down to the bottom because that's my Z value. I have a value of 1.28. If I have a two-tail, an alpha value of 0.01, so I go to my two-tail row. I go to my alpha value of 0.01, which is the very last column. Drop that all the way down to the bottom. I get this 2.58 or 2.576. Those are your critical values. These here are your critical values, but your critical values can also be found on your table here, and we'll utilize them. If your score falls into a critical region, once again, if your score falls into a critical region, you will reject the null hypothesis. If you go into a non-critical region, you will fail to reject the null hypothesis. If you fail to reject the null hypothesis still may be false, but there is not a significant evidence to reject it. We have Z star is going to be our Z test value. How we calculate the Z test value is the same thing we did with the central limit theorem. Value minus mean divided by standard deviation divided by square root of n. If you think back to the central limit theorem, this is what we did with the central limit theorem. X bar minus mean divided by standard deviation divided by square root of n. If we look at a one-tail right, what will happen? A one-tail right. What will happen is your critical value will go here. It's going to go on the right side of the bell-shaped curve. We have two regions. We have a non-critical and we have a critical region. If our test value falls in here, we fail to reject. If it falls over here, we reject the null hypothesis. So we have this critical value that we get from our table. We do a test value and determine which region do I fall in. If I fall over here, I fail to reject. If I fall over here, I reject. When we look at a two-tail, our critical values go here. And we go non-critical and we go critical regions. Go through the problems that you did for today in that worksheet and just tell whether they are one-tail or two-tail tests. That's all you have to do. Adios. Have a good day. Thanks,